Yeah, so today we will do the examples for 6.2 that we didn't do on Tuesday. So we'll go over them in detail, we'll work out the solution. And then after that, we're going to show you how to do a different way of measuring volume, and that's in 6.3. Um, so um, Remember, the big idea is that when we calculate area in 6.1, we needed to find the distance. We needed to find the distance between the 2 points. So um, if we are if we have a graph that look like this, yeah. So if we have a graph, so we'll start a little bit slowly. Yeah, and so if we have a graph that look like this, or two curves, and then the second one, let's say the second one moves like that. To find the area between the two curves, what we are going to do is we're going to measure these little rectangles. We're going to measure these little rectangles in between the two curves, and we're going to add up the area. And the way we add up the area is, of course, take the height, blue minus red, the y value for the blue minus the red y value for the red, and we're going to multiply by the width, and we're going to add them up. Here, what we're going to do is we're not going to do area anymore, but we're going to do solids. So instead of little rectangles, we're going to do little cylinders. We're going to cut them into cylinders. And in the idea of cylinder is that the two sides to two ends have the same shape. So if the top is like a hand, that top is like a hand, the bottom has to be the same shape. And all I have to do is take the area of my hand and then multiply by the height. Multiply by that. So that's what we're trying to do. Oh, angle is totally off. So that's what we're going to do. So instead of the height times the width, here we have the area. Here we have the area. And we're going to, and the area in this case is highlighted in red. And then we're going to multiply by the dx. And of course, that's dx. That's delta x. And that eventually, of course, lead to the same integral that we have, but we have the area inside. Okay. So that's a little bit of the theory. So the volume that we're going to be looking at are mostly the revolution type. So what we're going to do is we're going to take an area and then we're going to fan it across. So it's a little bit like a little bit like a little book, and then you can open it up and then close it on the other side, and that turns it into like a paper solid, right? A paper ball or something. So there's one type that look like that, and then on the assignment, we'll give you a different type that is not a revolution. And for that, we will do it a little bit differently, and we can do that with a pyramid and with a cone, and that's some of the common example that we will see. But for here, what we have is we have a rotation. And so eventually after we rotate, well, okay, angle's wrong. So after I rotate my hand like that, after I rotate it like that, I end up getting a solid. Each of the slice will be, each of the slice will be a circle. So you'll notice that each of these slice will be a circle. Oh, that's a terrible color. And in this slice, the radius of the circle is square root of x, because this point up here has the y value of root x, right? Because how do I know? Because over here, that's root x. And then down here below, that's 0. So it's 0 down here. So from 0 to root x is, of course, root x. Now, because I'm rotating it around, so if I want to find out, oh, what's that point here and what's the distance from there to there, because it's the same shape, even at that point, we're going to have the same, we're going to have the same, we're going to have the same shape that look like that, right? But just kind of sideways, we're going to have the same shape as this one over here. But it kind of rotates around onto the side. So if you look at any point on the circle, this is still root x. So it's a nice circle. Okay, so normally we don't draw that. So when I do my integral, here the integral is from 0 to 1 and pi r squared. So pi root x is my radius, and then square. And then we're going to do dx. Okay. And that's fairly straightforward. And of course, the root x here that's the radius, right? So we're doing pi r squared. We're kind of doing pi r squared. That's the area. In this particular question, root x squared is just x. So we're going to have pi times x dx. And most of the time, from 0 to 1, with the pi, we'll write it outside. It doesn't really affect this question here. But if we have a constant, we usually ignore it. We pull it to the front, and it's not involved in the derivative antiderivative process. Yeah. To find the antiderivative, this is x squared over 2 pi. And then we want to evaluate it from 0 to 1. And when we evaluate from 0 to 1, that means substitute 1 inside, 1 squared over 2, minus 0 squared over 2. And that's, of course, half a pi minus 0, so half a pi. So my answer is just half a pi. You notice as we go through these examples, we'll do the x squared, we'll do the power rule, the reverse of the power rule a lot. And of course, this rule is given to you in your integral table form. Right? So we can show you here. Yes, so the rule that we're talking about, the rule that we're using here is this one, where the power increased by 1. So it goes from power of 1 to power of 2, and we had to divide on power. So that's this question. Okay, so we kind of did it last time. So a quick review. We can do the same thing, but rotating a region around the y-axis. If we quickly look at the way the question is set up, sometimes you will have to draw it quickly in order to see what kind of shape we have. So in this case, y equal to 8, y equal to 8 is a horizontal line. Let's see which color do I want to use. So I'll use the horizontal line here. That's y equal to 8. X equal to 0 is a vertical line. So x equal to 0 is, let's use this, let's use purple. So this is x equal to 0. And then y equal to x cubed. So y equal to x cubed looks like this. Y equal to x cubed. And the area that we have, the region, is this region over here. And now, before we start rotating, it is very important to note this sentence here. It's very important to see that where it's going to rotate. And in this case, we're going to rotate about the y-axis. So what that means is that we are going to turn this way. We're going to take this and we're going to turn it this way. We're going to turn it on the y-axis. We're going to turn like that. And down at the bottom, we're going to turn as well. But at the bottom, well, there's nothing to turn. So it ended up being a point. So it will end up being a shape that look like this, kind of uh, like a drill bit or like a cup, a solid cup. Uh, yeah, so it will end up looking like. Now, as we look through our integral, so you notice when I cut, if I try to cut, if I have a cup like this, right? If I have a cup like this, it doesn't quite look like this because at the bottom it will have to shrink to a point, right? It'll have to shrink to a point. But you'll notice that if I cut sideways, if I cut from top all the way down to the bottom, if I look on the side, wait, let me finish the water first. All right, so if I cut on the from if I cut horizontally, wait, how do I describe this? If I cut, so the way we would describe it is this line going up and down, going up and down. This is the y-axis. So if I slice along the y-axis, so if I'm slicing along the y-axis, I'm going to get a cut. I'm going to get a circle. So circle is good because we know how to calculate the area of a circle. But if I try to cut in the x-axis, so if I'm trying to cut from the x-axis, and that will go from this way, cut like that. If you actually slice it down and you look on the side, right? You look on the side, you're going to get, right? If I cut and I show you the cup on the side, it's going to be not a circle, but a strange shape. And this is hard to calculate. We don't know what the area here is. Okay, so we don't want that. So in this question, when we are rotating about the y-axis, we have to do dy. If we're rotating about the x-axis, then we do or anything with a horizontal axis, then we will have to we cut with along the horizontal axis, along those axes. So if we're rotating about the y-axis, we have to cut along the y-axis. So this way, and one of the easiest thing to remember is if I am moving vertically, if I'm rotating about a vertical axis, then I have dy. In this case, because I'm going from 0 to 8, right? The y value is from 0 to 8. That's the limit. When you look at the radius, so always think about what the radius is. So the radius would be somewhere from here, right? All the way out to outside to out here. So this is the radius. So going from the axis, the y-axis, to out here, that's the radius, that's r. So what's r equal to? R is equal to x squared minus 0, right? I mean, that's just x squared. Because we start from 0, we go up to x squared. So I'm going from 0, I'm going up to x squared. So the radius is just x squared. So this is pi. And then we have x squared. Oh, but we don't actually want to do x squared. Oh, hey, there's something tricky here. Oh, and this is cube. Sorry. We don't actually want to put x equal to x cubed inside because we have dy. Okay. So the y value itself. So if we think about the value here, okay, if we think about this point, if we think about this orange point here. Okay, so I'm going to say that's not right here. And I'll tell you why. Because the y value here is 8, but the radius is not 8. The radius is actually what the x value is, and the x value down here is 2. How do I get the x value? How do I get the how do I get the how do I get the x value? I have to take the y value, right? I have to take 8, and then I have to cube root it. So what we're going to do is we're going to take this, before we put it in, we're going to solve for x. We're going to say that x is equal to cube root of y. So you can write it like that, or you can write it as y to the power of 1/3. And of course, we write it as 1/3 because 3 of these multiplied together give you back your original y. So 3 of these multiplied together to give you your original y, and that gives you a power of 1, and they add up. So each of them is 1/3. Okay. Another way to think about it is because I'm doing dy, I need a y value. Well, not quite. I need to have variable represented in terms of y. So I'm going to represent my x value in terms of y. But that's not a good way to think about it. You should look in your graph and realize that your radius is the horizontal distance, is the distance in x between x equal to 0 and my blue line. So I need to solve for x for my blue line. The blue line has the x value of y to the power of 1/3, and we're going to put that in. So that's the tricky part. You have to don't just take your function and just stick whatever is inside. Look at whether I need the x value or the y value. In this case, I need the x value because my radius is going sideways. Okay, once we have that, we'll have 0, 8, pi, y 2/3. Normally, we will put the pi outside. I kind of forgot. That's okay. Let me put it outside right now. Because it's a constant, 0 here. We can integrate this. We're going to take the power and add 1. Right? When we do the derivative, we subtract 1. So when I do the antiderivative, when I do backwards of derivative, inverse of derivative, I'm going to add 1. So this is y to the power of 5/3. And what we're going to do is we're going to have 3/5 on the bottom. And you can always double check the derivative of this is going to give you that. Right? The derivative of this, 5/3 comes down. Cancel out the 3/5. So that's why they're reversed. So I can write it like that. I don't have to, if you write it using the formula and have 5/3, it's really confusing because you have fraction within a fraction. So it's a little bit easier to just kind of remember that I'm doing the backwards one and just make sure after you do the derivative, the constant factors in. So we have the pi here, and we're going to have 0 and a. So this will be pi times 3/5, 8, 5/3, minus 3/5, 0, 5/3. Now you don't have to write the 0 part because this part is just 0, right? The end is just 0. So you don't have to write it if you don't want to. You can just write 0. Or don't write it at all. That's okay too. 8 to the power of 5/3. You can use your calculator, but this means 2, right? Because cube root is 2, and then power of 5. So 2, 4, 8, 16, 32. So I will have 3 times 32/5 times pi, right? And then minus 0. And that's, of course, 96/5 pi. So this is the answer. And you'll notice we'll almost always have a pi in the front because we're doing circle. So pi comes up in the area and in the volume, right? If you think about area of a circle or volume of a ball, of a sphere, or volume of a cone, right? Circular shape, or volume of a cylinder, they all have pi in there. One of them, because we have these surface area. Okay, so that's the process. Now, just to help you think about the question. Oh, I don't want to press clear. Okay. If we spin this in different ways, we're going to have different functions. We're going to have different integrals. So let's take a look at some of the examples. Okay. So I'm going to erase these. Let me know if you need to take a screenshot. I can always undo it. But this first example is in what I wrote down here so far. They're all in your notes. Yeah, and if you have questions, you can stop me anytime. Okay, so what happens? So what would the function look like what would the integral look like? You don't have to solve it, but I want you to write down the integral. If I'm rotating about the x-axis, and then we can also rotating about y equal to -1. Let's try that. And let's rotate about x equal to x equal to 3. Let's try that. X equal to 3. Right, so we'll have a couple of different ones. And so this exercise here, we're just trying to come up with the integral. If I'm rotating about the x-axis, if you're rotating about the x-axis, that would be, hold on. That'd be a little bit hard. Wait, before I go on, let's instead of y equal to -1, let's do y equal to 8, just so that the calculation will be easier. Okay, let's start with the rotating about y equal to 8, because this one is easier to do. Rotating about the x-axis turns out is not easy. So let's start with rotating about y equal to 8. Now, let me see if I can call out my picture. Okay, so I'm going to use the picture here. But I'm going to erase my ugly shape. And we're going to use the real picture, and then we are going to go through these examples. Okay. So let's start with rotating about y equal to 8. And I'll put the other two down here. If I'm rotating about y equal to a, so this is y equal to a, so that means I am going to take my, let me see if I can take my hand. So y equal to 8 is above here. So y equal to 8 is above here. So I'm going to spin my shape up and down like that. Okay, because this is going to be the axis. So the axis doesn't move. So I'm moving around the axis. If that's the case, then the shape will look a little bit different. The shape will look something like this. So I'm going to use the yellow one or let me see if I can use ice blue. So I'm going to rotate it. So on the top, it's not going to move here. And then, can't really use that color. So I'm going to use green. Okay. So on the top, this point, there's nothing to change here. But down here, so this point, because we have this whole thing, that will rotate all the way up, right? And then come all the way down in the back and turns into, yikes, my drawing skill is terrible. Okay, so let me draw it like that, and then it will kind of come back in like that. Okay, and then of course we're going to have the same we're going to have the same function. We're going to have it the same function on the other side, right? So we're going to eventually turn into something like that. Now, unfortunately, what I think I'll do is I'll fill it in. It might be a little bit easier if I color it in. Yeah, the coloring is always a little bit difficult. So you can imagine that we have like like a surface at the bottom. Yeah, it's a little bit odd. Probably made it with. Probably made it with. I'll just leave it like that. And then later on, somewhere in the middle, there's a smaller circle. There's a smaller circle that will go up to the other side, kind of like that. Not great, but you'll sort of see that it's more like a sideways. It's more like a sideways shape. Wrong angle. Sorry. Yes. Yeah. Right. This shape. Yeah. So it'll be more like this. Whoosh. Oh yeah, it's kind of hard to see. Okay. Because I'm rotating like this, then you'll notice the axis is this one. So in this case, the axis is down the center like that. Because the axis is down the center like that, horizontal axis, we're going to use dx in this case. The radius is going to be the distance. The radius is going to be the distance between these two things, right? That's the radius. So between A and my function, so I'm going to do 8 minus x cubed. And I'm going to write square inside, and I'm going to put the pi. Yeah, so that turns out to be what this rotation would look like. So this is from 0 to all the way up here 2. Okay, so that would be what it looked like. So you notice a few things, a few differences here. Here we have dx because our axis is horizontal. Our axis is horizontal, so we had to cut. We had to cut perpendicular to the axis, so we're going to get dx. Horizontal axis, dx. Besides that, when I calculate the radius, it's not just the function, it's the distance between 8 and that function. So it's going to be 8 minus that. Just like when we do the area, we take the bigger function up top minus the smaller function on the bottom. So if I'm rotating about y equal to 8, that would be the setup. If you need to integrate it, right now you can't integrate it. So if I need to integrate it, I will have to go from 0 to 2. I'm actually going to expand the terms. So 8 times 8 is 64. 64 minus the middle term. So 816 x cubed plus x to the power 6 dx. Then we can find the integral after. Right, so it's I apologize, my shape isn't the best. Didn't draw it very well. Okay, now what happens if I rotate about the x-axis? So if I wait, I need to keep something disappear. Okay, I need to keep that on the left. Oh, okay. So if I'm rotating about the x-axis, I'll leave that on the top first. This is the x-axis down below. We're going to rotate the shape onto the other side. So what I like to do is I like to draw like the same shape on the other side. That helps me, for me, it helped me visualize a little bit. Okay, so if I know the same shape on the other side, it helped me visualize it a little bit. And what happens is we're going to rotate it. We're going to rotate it around. Um, and so let's see if I can draw it. So we're going to rotate the base. So this is what the base will look like. The base will look something like, okay, very ugly. So how about this? I'll draw the little red slice in the middle. I'll draw the little red slice in the middle. I'm going to use pink to see if I can do that. So if I look at this point, if I look at what happens in the middle, if I look at what happens in the middle, then there are two things. There's a bigger circle on the outside, right? If I look at what happens in this cut somewhere in the middle, in the slice, I'll have a big circle. I'll have a big circle. And then inside, I have a smaller circle, right? Because as I kind of cut through it here, there's a smaller circle, right? And our area is everything in between. Our actual shape, so our actual shape is not a solid. There's actually a little dent down the middle, or the other side. There's actually let me see if I can do it vertically. I had to point there. Okay, so there's actually a little dent down in the middle. Down in the middle. Wrong side, wrong direction. A dent down. Like that. Yes. Okay. It's a little bit hard to do it on the. Yeah. So there's a little dent down the middle. Um, it's kind of hard to show. I wish I have some clay. Oh, that's a good idea. I should get some clay. Yes. And so we have two different circles, and then we have to kind of imagine what's in the middle. We're going to imagine what's in the middle, and the middle is, of course, the middle is everything in between. But we're missing a circle down here. We're missing the circle. We're missing the circle. So that's the area of my cross section. That's the area. So let's write that down. We don't have to evaluate it, but I want you to be able to set up. So yeah, a type of question would just ask you to set up and not ask you to evaluate. So in this case, what we'll do is we'll do the big circle minus the small circle. So I have to do big circle area minus small circle area. So that's normally what we would do. I'll use it. I'll do a different color for this. Okay, so big circle area minus small circle area. So we'll do pi. And then we'll do, now you can do pi r squared for both. Normally we will pull out, okay, wait, let's not do that at the beginning. So let's do just pi r squared minus pi r squared. For the big circle, you'll notice the top is always at 8. So the big circle on the outside, it's going to go across. It's going to go across, and it's always going to be a radius of 8. So pi 8 squared. Now the inside, the radius is a little bit smaller. It's a little bit smaller at the beginning, and then as it gets closer to 2, it gets very big and open up very wide. The y value is x cubed. So here we have x cubed. And then we have dx. So this is the setup, and we're going from 0 to 2. And we know from 0 to 2 because the intersection here happens at the point of 2. So that's big area minus small area. Then we'll do that. And that's just a constant. That's just a constant. So when you integrate it, it's 64 pi. So you'll do this, and You pull the pi to the front, 0 to, you have 64 minus x cubed, and then dx. And then just a reminder, when you integrate it, this just becomes 64x, and then the back becomes x to the power of 4 over 4, right? 64x, so you'll get 64x. And then minus x to the power of 4 over 4. Of course, you'll still have your pi, and then you have to evaluate from 0 to 2. Okay, so that's the set. So you'll see that even though we have the same area, but depending on how we rotate it, we are going to have all sorts of strange, we're going to have all sorts of strange shape and strange values, and strange values, and strange integrals, etc. Okay, let's look at the last one. Yeah, and once you understand it, it's really not that hard. Right? And so the other example in the back, some of them have the washer system. This is the washer example where you have a little hole in it. Okay, now if I rotate it about x equal to 3, now remember here, right here, the x value is at 2. So if I'm rotating about x equal to 3, this is the axis. This is the axis that I'm rotating about. So my area, the area so the thing that we're going to rotate it, once we rotate it, once we rotate the area, we're going to have this shape on the other side. So we're going to have kind of like the same opposite shape. And we're going to rotate it around. So if you look on the top, if you look on the top, you'll see, you'll basically get a little tube, right? You'll get a little tube. You'll get a little tube. And you can sort of see that this part is my tube. Okay, that's filled in. That's my tube. That's my wall. And as I go straight down, my little tube is going to get thinner and thinner and thinner, and then eventually the wall is gone. So at the very bottom here, there's really no volume. Okay, there's no volume on the bottom, on the last layer. Almost zero volume. Right, so we'll have something like that. But you can see how you are going to calculate the size of the washer. So here, when I calculate the size of the washer, something's not right there. I'll integrate, because I'm doing dy, I'm going to go from 0 to 8 dy. And we're going to go from the outside. And you'll notice the outside is always the same, right? The outside goes straight down. The distance is always from 0 all the way to 3. So here, this is pi 3 squared. And minus pi. And then the inner distance is the distance between my curve. My distance between my curve, x equal to cube root of y. And 3. But 3 is larger, right? 3 is larger further to the right. So I have to do 3 minus cube root of x. Oh, very messy. So you need this. Yeah, so in this case, we won't ask you to calculate because this will be a big mess. But you could still calculate it. There will be 2 terms left after you expand the bracket. So it's not too hard, but it's something that is a little bit messy with all the cube root and squares. Yeah, so that's how we could have different integral, different volume, different shape. If I spin it rotating about different axes. Okay, so this is important. We'll give you a question where it's where you had to calculate the volume uh, when we rotate the region. Okay. Now this part, these three example, I just came up with it. They're not in the notes. So if you like to take a screenshot, now so you can do it now before I go on. So this next example, we just want to show you that here we're going to get the washer shape. Here we're going to get the washer shape. So here we have a curve. Now, if it's not very obvious, the first step that you should do is find the intersection point. So you know that it starts from 0, go all the way up to 1 for both X and Y for our shape. And here you can see in a much better photo that we are getting these little washers. So we're getting these little washers. But what you can imagine is as I'm spinning it around, as I'm spinning it around, as I'm spinning it around, it's a little bit like, people who are doing pottery and they're on the clay and then the pottery wheel is spinning. And so you're doing that and you're kind of holding this shape and you'll eventually get a little cup, right? You'll get a cup or a vase. A container shape. And so that's what we're getting. And the shape of the thickness of the thickness of the container is basically how wide the wall is in between the two curves. And that's what we're going to do. And we're going to take the big circle minus the small circle. I won't say too much about this specific question because the concept is the same. We did that previously. But what I want to show you today is another version of calculating the volume. So there's another version of calculating the volume. This one is not as common because most of the shape that we deal with, if you think about spheres or cones or cylinders, we can find them very easily by this rotation method. Now, the shell method is a little bit different. It deals with shapes that have a slightly different symmetry and a slightly different method of rotation. So let's imagine that here we have a region. Here we have a region, and we're going to rotate this region about the y-axis. So here we have the y-axis. So here we have the y-axis down in the middle. And we're going to rotate this region. So what we are going to do is we're going to have like a lighter color in the middle. So I'm going to do a lighter. Oh, wait. What I like to do is I like to draw the same shape on the other side. That for some reason that helped me visualize. So I usually like to draw I'm not very good. Okay, so usually I like to draw the same shape on the other side, and so that it can help me visualize. If we look at this slice, if we look at the slice that's given here, you'll notice that there's an inner part, there's an inner circle. So this is the inner circle. I'll do it in purple. So it will go from this point, that point. It will rotate to the same spot on the other side on the mirror image, and we're going to have a little circular hole. And then the outside, we're going to get a bigger solid shape. We're going to get a bigger solid shape, and I'm going to use a different color here. And we're going to get a bigger solid shape. All right, so as I slice it across, as I slide this rotation across, I get a little washer. So washer is this metal piece, right? If you have nails, you have a little metal piece that have a hole in the center. So you have this donut shape. In this donut shape, what you will see here is that in order for us to find out the size, the radius of these circles, I need to know the x value here and then the x value at the other point. So I need to know these two x values, these two. That's how I find the radius, right? Because this is the radius for the smaller circle. And of course, the bigger circle has the radius all the way up to the other side. For us to find the radius, we have to solve this equation, right? We have to take this equation, find out what x is equal to. That's kind of hard. That's really hard. I mean, that's really hard with y inside. Um, and so we aren't able to do that. We can't do this easily. This is very hard, trying to find out what x is equal to. So we're not going to solve this question this way. We're going to think of another way to solve this question. And this is what we're going to do. So we're not going to solve it like this. What we're going to do instead. Oh, by the way, this shape that we're finding, eventually it's going to look like this. So we're going to, this is the rotation shape. And once we rotate it, it looks like a little bowl. It looks like where your dog or your cat is drinking water from. It looks like a little pet bowl. Yeah. So that's what it looked like. And you can see the red contour, this red curve that is given to us. Okay, and once you rotate it. What we're going to do, instead of doing a slice and doing a cylinder, we're now going to do like a ring shape. We're going to do a ring shape. We're going to do something called a cylindrical shell. And if I need to find out what the volume of this shell is, what I'm going to do is we're going to imagine a big one on the outside. We're going to imagine a big one on the outside. And I can find the volume. The volume is pi r squared h. Right, that's the volume. It's the radius, right, times radius squared times pi. That's the circle times the height. And then what we're going to do is we're going to find the cylinder on the inside, the volume of the cylinder inside. So we're going to find this one here. So the smaller one. And the smaller one will have a different radius, a smaller radius, but the same pi r squared h. So circle on the bottom times the height. Now, of course, the pi and the h are the same. It's really the difference of the radii. I have the difference of the radius square. And what I can do is I can write it as r, the two of them added together, and then the two of them subtracting each other. The difference, and the difference, the difference of squares. You'll notice that this part is the thickness. This part is how thick the cylinder is. This is how wide my cylinder is. And if I'm talking about how wide I move across as I go and do the next slice, we will ended up calling this as dr or dx or dy, right? So we'll call this d something. And you'll notice this part in the front, you can imagine, we can sort of imagine that if I add a 2 here and multiply by a 2, this is the radius. This is the radius in the middle. This is sort of the radius in the middle. And then if I do 2 pi r, this tells you, this kind of tells you how long the circumference is. So it tells you how long this, wrong color, not a good color. So let me do a different color. So it tells you how, I'll use purple. It tells you how long roughly uh, this surface is. So imagine you bought a Swiss roll, you bought a cake that is rolled around. Well, how much volume is in the cake? So it's an empty cake, nothing inside. We're just talking about the cake, not the filling. Okay, so you got a cake that's rolled around, that's rolled around like a circle. So how much volume it is? Is it what you'll do is you open the cake up, right? So you open the cake up, right? And the length of the cake would be 2 pi r, right? 2 pi r. So that's 2 pi r. So that's the circumference multiplied by the height. Multiplied by, oh, sorry, the height goes this way, right? So once I'll use one hand. Okay, so once this is my cake, this is my cylinder. So that's my cylinder. If I if I open it up like this, if I need to find the volume, this part is 2 pi r because it was in the circle, right? And I open up, that's 2 pi r. And then this piece here, this side here, this side is the height because in my cylinder that look like this, going up and down, that's the height. That's the second part. And then once I open my hand, I also need to know the thickness. The thickness is, of course, the difference in the circle, right? So if I have the thickness here, that's the difference between the radius. So that's the last part. So it turns out the volume of these shells are circumference, height, thickness. So it's a little bit harder than pi r squared. It's a little bit harder than pi r squared. Yes. And so what we're going to do, this bowl shape that we have, the bowl shape that we're going to have, we're going to take each of these cylindrical shell, we're going to take a cylindrical shell like this, and we're going to make many of them. And we're going to add up the volume and do the integral. So what we're going to do is we're going to do 2 pi x, that's the circumference. So 2 pi x is the circumference. It tells you how long this thing is going across. Times times f of x, that's the height. Times dx, that's the thickness. So that's the three sides. Circumference, height, thickness. And we're going to do an integral like this. And you'll notice as I go across, as I go out, I don't need the horizontal distance anymore. I don't need the x value. I need the y value. I don't need the actual x value, but what I need is I need the y value here instead. Okay, so in that example that we had, we have our shape like this. When I look at each of my slices, the circumference, the length as the circumference, so the total circle length of my slice is 2 pi x. We can leave it like that, and that's not an issue because we're going to do these cylinders going from 0 up to 2. We're going to cut it in the x direction. So we can just leave the x as it is. We don't have to convert the x to y. So that's the benefit of this part. We know how to calculate x. We know how to put x in. And that's great because I don't want to solve for y. I don't want to write it in terms of y because I can't do it the other way. I can't write the x in terms of y. Okay, so I'm going to have that. And then the height is 2x squared minus x cubed. And then we have the thickness. Thickness is dx. So you can think about the shell method instead of finding the area and the slice, we're doing the area of this little we're doing the area of this little piece of paper wrapped around this little shell. We're looking at the surface area of this shell. Yeah. Okay. We'll multiply these together. Then we'll multiply the terms together. We'll get we can leave the 2 pi outside. They're just constants. We only have to multiply the x inside. So 2x cubed minus x to the power 4. If you want, you can break it into two. You can break it into two different integrals. When I integrate it, um, this first one becomes 2x to the power of 4 divided by 4, right? Because I take 3, I add 1. And instead of writing it like this, I factor out the 2 and the 4. And so I'm left with just a 2 at the bottom. The second term is just x to the power of 5 over 5. Now we'll substitute 2 inside. If I substitute 2 inside, I get 8. And then 32 over 5. And if I put 0 inside, I get 0. So I didn't write that down. And once we subtract it, we get 16 pi.